Okay, hello everyone. This is additional video for 2.6, the precise definitions for limit at infinity. So let me just give you a brief descriptions on the precise definitions. Remember the epsilon and delta. So let me write a precise definition. Let me make it zoom bigger. Precise definitions. For limits or for limit at infinity. Okay, let me write the definitions first. Okay, so first let the function f be a function defined on interval a to infinity. Now then we have the limit as x goes infinity of the function. This will be resulting in some L. So it means, okay, so it means in the precise definition, okay, so means for every epsilon positive, remember that epsilon is the distance between the f of x and L, okay? So, or there is corresponding number, we say n, okay, for this number, such that, okay, such that the number n, so if we increase the x, okay, increase the x greater than n, then for sure the distance between the f of x and L, they will always less than epsilon, which means that when we increase x larger and larger and larger, and we can symbolize that with our infinity, then the distance for f of x and L, they will have the same, not the same, they will have some certain distance which is always less than epsilon, okay? Which means that their graphs or their curves, they will go into some point that we usually denotes the point or the line as the horizontal asymptote, okay? So if we graph, let me just put the graph that I have, take the screenshot for you. Okay, now what this word means, this x greater than n and this n, so every epsilon positive, there will be some n. When we put n anywhere we would like to, like we can put n here, we can put n here, here, or for our illustration, let's just put n, let's put n greater and greater and greater. So for example, we take the n maybe here. So if we take the n here, so if we take this as our L, our corresponding L here, it means that the range for its epsilon, there's always between this distance here. Okay, either it's L plus epsilon or L minus epsilon. We should always know that there is a small distance epsilon between L and the function, okay? And when we may be taking greater and greater, maybe here, we still have that the corresponding L is inside this range. It's inside this particular distance epsilon, okay? Which means that it's going to be our proof that no matter the graph will be, if we have this condition that we have the limits at infinity, when we take x as larger as possible, we are going to have a distance between the f and the L. They will always have this epsilon value, okay, that there will be a consistent, that there will be a consistency on this epsilon value, okay. Okay, so maybe if we take a more a closer look at the same graph, but we take the greater n. So let me erase this to make sure. So we take n larger, and you will see that, okay, we are now have this this range here, and of course the range is still in between this epsilon. Okay, so epsilon, they can be a difference according to this n, but we will have those consistency in this proportions. Okay, this the distance between the f and l. Okay, in the same way, if we let me take a new page. Okay, I think if you want to take notes, you can just pause the video. Okay, so let me add another notes. Similarly, if we take the let me write the words, be a function define on, now we take from the farthest left into some a can be any number, then we say the limit as x approaching negative infinity, we are now going to the left, okay, negatively large for x, but we have still the same definitions. Okay, so it means for every epsilon that is positive, there is a corresponding n such that if x, or now it's not greater, but it should be less, okay, because we are going to the left, I forgot, okay, going to the left, we will have the distance will always be in terms of epsilon. Okay, now if we take the graph, let me take the graph. Okay, now similarly it's the same as the previous one, but now we are going to the left. Okay, so we are going to have x less than n. So we can start from here if you want to make it more clear. You can start from here. This is L, and then we have the epsilon, and then we can move to the left, and then maybe start going to here, and this is what we have. Okay, and when we move, we see that it's going to approach this L, and we have this the distance between L and the function or the curve f. Okay, so we are going to have this plus epsilon and minus epsilon for this range. Okay, all right. Okay, now how to look on the formulation in mathematics. Okay, so if we take this, I believe we now already learn how to compute this. So basically we have, so let me start with just a little bit review. Okay, when we have this rational, we have limits at infinity, right? And the first thing you need to observe is we have the same degree, okay, the same degree of power, okay, which means this is the quadratic degree, the power of 2 for the numerator and the denominator, which means that if we are going to divide all with 1 over x squared, and we can do that all, of course, then the rest of the equations beside the highest one, which is the power of 2, will become 0. Okay, So I hope you get my point. So this will be getting to 3 over 5, right? Okay. Now we know this from our computations, okay? But how do we prove that this is true in our precise definitions? Now that's the different story. So relate this statement, relate this value L 3 over 5 with the epsilon 0.1. So let's say we are going to have our epsilon restricted to 0.1, and then we are going to prove that this statement is true. So we are going to start with, so if x is greater than n, then we are going to write a function. Let this is a function, be a function. Okay, so let the distance between the function, let me write the function. And then 3 over 5 we can write as 0.6. Let me write with 0.6. And this should be less than the epsilon, which we assume as 0.1. Okay. So we expand this absolute value and we write in terms of inequality. Let me write the equation first. Okay. And this will be 0.7 and this will be 0.5, right? Now, the best way is we may need to look at the graph, okay? At the graph, maybe let me take the graph for a while. Okay, and then we take some approximations, some estimations for this graph. So yeah, this is just an illustration to see what x should we write off into our equation. So if we take this and we see that our curve, this red curve here, is in between a 0.7 and 0.5, okay? So if we take y is 0.5 and we try to find what is exactly this point, okay? We find that if using the graph, okay, using graphing calculator for y equals 0.5, okay, we get x is around 6.7, okay. So if we would like to have the point, okay, let me put into green. So if you would like the points maybe around here, then perhaps it is safe to say that if we assume x equals 7, then the case will be true, okay? So if x equals 7, then the rest of the equations, and we write as this, okay, this original equation, this will minus 0.6, then this will be true. This equation will be true. So when we have x equals 7, then this will be true. Then this equation is true, okay? So in other words, for epsilon 0.1, as we assume from the beginning, we can choose n equals 7 or any large number. Okay, another proving that perhaps we can see some principles, okay, for your understanding and in calculus is 1 over x. Okay, so I believe this is just to show you how the precise definition works. So basically, we are going to find the n, okay, in which when we increase the n, it is going to be perfectly in between this. So the curve will be in between of the approximation, our approximation that is 0.5 and 0.7, and 0.5 and 0.7 is come from this epsilon 0.1. Okay, so we can start from perhaps assuming that the epsilon is really small, maybe 0.1, maybe 0.01. It's up to you actually, just to set up with something. Okay, and also it depends on some conditions. As long as we can fit the conditions and we see how it works, okay, and we get this inequality, then we can find which value that is in between 0.5 and 0.7. Okay, so we could find y. Okay, we could find y in between this 0.5 and 0.7, and from that y we get some x. Okay, in our case we get the x is we get from this y 0.5 first, and we get this 6.7 around, and it's safe to say that if we increase this x, the point will be in between this this condition here, which is perfectly fit with our definition on precise. Okay, I hope you get my point. Okay. Okay, now now another thing is the 1 over x. Let me give you the limit. Okay, of course we know that this is from our computation and definitions. This is equal to 0. Okay, so to start with, to prove this, okay, so proving this statement. Okay, so to prove this, we start with the epsilon positives. Okay, so given epsilon is positive, need to find n such that, so again, in limits at infinity, we are not going to find the delta because we are having infinite amount of x, so, which means that we are going to find n that is correspond to these functions. Okay, so if we have this, and if x is larger than n, okay, then the distance between the functions and the L we assume, and we because we need to prove this, so we take the 0, and this is less than epsilon. And assuming that x is positive, so it's going to be on the right side, then we have 1 over x is less than epsilon, or x is greater than 1 over epsilon. Okay, now because we have this, so it's obvious if we choose the n is 1 over epsilon. So choose n is equal to 1 over epsilon. So if x is greater than n and n is 1 over epsilon, then the statement of this, right, this becomes 1 over x less than epsilon. Oh, sorry, this should be equal. Therefore, as a conclusions, the limit for 1 over x is equal to 0. Okay, so no matter how much x you have, if we have this limit as x going to infinite number, then we are going to say it's equal to 0. Okay, and based on this epsilon definitions, no matter what the n value is, as long as we can find some x that larger than some n, we are going to have these conclusions. Okay, because we always have the x is greater than 1 over epsilon. Okay, so if we take the illustrations on what n or how the n will fit with the precise definitions, okay, we can take that, and let me take this here. Okay. So we can imagine, okay, we can start, let's say, take n equal 1, and it become epsilon 1 and n1, right? For at n equal 1, epsilon is equal 1, and when n equal 5, you will see that the epsilon is 0.2. It's 1 over 5, right? 1 over 5. It's precisely similar to what we have here. Okay, so whenever we have n, the epsilon will be 1 over that n. Okay, and when we have this n is equal 10, this will be 0.1, and it will be having this notions that the distance between f and the L is always it's 1 over n. Okay, I hope you get my point here. Okay, one more thing, last one, is when we have the infinite limit at infinity. Of course, it starts with let me write, let f be a function defined on some interval a infinite, then this will be infinity. It means for every it's not, my writing is not really good. For every positive number m, okay, there is a corresponding positive number n, okay, such that if x is greater than n, then f of x is greater than m. Okay, so how to understand this statement? First thing, let me and maybe a little bit upwards here. Okay, so maybe it's going to be up here, maybe getting smaller. Okay, so what does it mean? Okay, so it means if we have some positive number m, okay, there will be n, okay, such that so if we take the n, okay, if we take the x is larger and larger and larger, so x will larger and larger, the result is there will be no restrictions, there will be no getting close to some value for the f of x. Rather, the f of x will have this m that is always greater than its function. So the notions is the curve will always getting larger. So when we have x larger, the f of x also getting larger. So that's how it is, and we kind of precisely define those large number as the n and m. Okay, so n and m, it just symbolized that when we took that number, there was always another number that is bigger than the functions. Okay, if we took the graph, this is how it looks like. Okay, so every time we took the n, okay, every time we took the n, let's say here, the corresponding is always going to be here, m. So it's always going to have another corresponding that state that it's always getting larger. Okay, so when we increase n, the m also getting increased, and we can imagine that if we took the limit, then the results will be another infinity. Okay. Okay, that's the precise definition for of infinite limit at infinity. Okay, so I think that's it for additional notes. Okay, hopefully it can help you to understand the precise definitions. Okay.